Right, so we finished last time talking about Lr circuits. And we just need to finish talking about all of the circuit combinations that we can have. We've talked about RC circuits, we've talked about Lr circuits. Next, we're going to talk about LC circuits, and then we're going to put them all together and talk about Lrc circuits. So let's start with LC circuits. So an LC circuit is probably, as you might guess from the name, it is a paired inductor and capacitor in some arrangement. So the picture here is maybe you have a capacitor, maybe a switch, and then an inductor. And maybe the capacitor is initially charged. The inductor has inductance L, the capacitor has capacitance C. And so before the switch is closed, we can actually describe the charge on the capacitor. So the charge on the capacitor at t equals 0, and we're going to assume that the switch is closed at t equals 0. This is equal to Q naught. It's just some initial charge, right? So the question is, what happens when the switch is closed? What happens after t equals 0? And at this point, we have the tools to handle this. So we're going to use the loop rule. We're going to use the Kirchhoff loop rule. So using the loop rule, so we choose. This is an arbitrary choice I'm making, but I'm making the choice. We're going to choose counterclockwise for our loop direction, and we're going to guess that I flows. So remember, when you're doing the loop rule, you always have to specify a direction for the current. And then when you're doing the loop rule, you have to choose to go either clockwise or counterclockwise. I'm going to guess that current flows counterclockwise, and I'm also just going to choose a loop that's counterclockwise. So that leaves us with the following. So we have Q over C. So if, say, we start top right, we pass by the capacitor from right to left because we're going counterclockwise. So because the positive side is on the second side that we get to, the voltage goes from low to high. So we have a plus Q over C. And then we have to think about what happens for L. So for the inductor, we know that the current is initially 0. So that means that the inductor, and then the current's going to try to increase once the switch is closed. So the inductor is going to try to keep the current low. What that means is that the inductor will, right when the switch is closed, the inductor will produce an EMF that's oriented this way. So it will produce an EMF in the opposite direction as the current flow to try to reduce the current flow. So that indicates to us that as we go around, we would have a minus sign because we're going from the positive side to the negative side of the inductor. So we have Q over C minus L di dt. And the EMF induced is just L di dt. And so we just had to figure out whether it's positive or negative. And so now we just need a quick reminder here about how the charge on a capacitor relates to the current. So recall that the current flowing into or out of a capacitor is the rate of change of charge in that capacitor. In this case, the current is the charge in the capacitor is decreasing. Oh, am I recording? Yeah, the charge in the capacitor is decreasing as the current flows in the positive direction. And so that gives us here that the current is the negative rate of change of the capacitor, of the charge on the capacitor. The rate of the charge on the capacitor decreases, so dq dt is negative, but we want the current to be positive in the counterclockwise direction. So we multiply dq dt by a negative sign to get the correct sign. So now our equation becomes the following. We replace di dt we replace the I in di dt with negative dq dt. So we're left with this after doing some rearranging. We get d squared q dt squared plus 1 over LC times q of t equals 0. Now, what I've done is I've substituted in this I here, so that's how we get the second derivative. And then I've divided through by the L, and the two negative signs cancel out. I've just done some simplification here. But this kind of equation should look familiar to you guys. This is the equation that governs simple harmonic motion that you may or may not have seen in 9A. So the differential equation for simple harmonic motion is 2 derivatives plus a constant times 0 derivatives equals 0. And the solution to that differential equation is very well known. It just depends on that constant there, 1 over LC in this case. And so the solution here is Q of t is Q naught times cosine of omega t, where omega is 1 divided by the square root of LC. That just is the solution. And if you're curious, what you can do is you can take this, plug it in here, plug it into the Q for both places. You'll have to take 2 derivatives and you'll have to plug in what omega is, but you'll find that this function does satisfy that differential equation. So that just is the solution. And so from that result, we can actually use the fact that the current is the negative time derivative of charge to find the current through the system. This gives us that the current is negative, the negative sign cancels out with taking the derivative of the cosine. So the current is Q naught omega times sine omega t, which can be simplified to Q naught over square root LC times sine omega t. And then we just label Q naught over square root LC as I max, where I max is Q naught over square root LC. And it should be clear why I max has that value, and that's just because that's the coefficient in front of the sine. And we know the maximum value of, we know that sine and cosine, their maximum value is +1, their minimum value is -1. So the most current that there could ever be flowing through the circuit is Q naught divided by square root LC. And so that's why we label that I max. So really what happens is you have charge on the capacitor, that charge drains, and it becomes, and then that charge will go back and fill up the other side, and then it'll oscillate back and forth as described by this function. So let's ask the question about energy. So because we know capacitors store energy, we know that magnetic fields store energy, inductors store energy. So we should be able to account for all of the energy in the system. So at t equals 0, the current is 0 just by looking at this equation. If you plug in t equals 0, sine of 0 is 0. The current is 0, and the charge is Q naught, which is just the maximum charge. And so what that means, we know that the magnetic field in the inductor is proportional to the current flowing through the inductor. And we know that the energy is proportional to the magnetic field squared. So if the current through the inductor is 0, then the magnetic field is 0, and hence there's no energy stored in the inductor. And in particular, the amount of energy stored in the capacitor is at its maximum because the energy in a capacitor is proportional to its the square of the electric field, and the electric field is proportional to the charge. So if the charge is at its maximum, so is the energy. So in this case, at t equals 0, all of the energy is in the capacitor. And that's not surprising. The capacitor starts out charged before the switch is closed, and the inductor, there's no current flowing through the inductor when the switch is closed, so there'd be no energy there. At a later time, at t equals, say, pi over 2 omega, so this is just this is a quarter of a cycle through. So you could imagine plugging pi over 2 omega into the current and into the charge. We find that the charge is 0. That's because if you plug that into cosine, you would get cosine of pi over 2, which is 0. And you would find that the current is maximum. I is equal to I max. And so what that means, well, if the charge is 0, then there's no energy in the capacitor. And by energy conservation, all of that energy has to have gone to the inductor. And we find that the energy in the inductor is at its maximum value. So that's not surprising. And then we can go further. We can ask at t equals pi over omega, the charge is negative, the maximum charge. So the charge polarity of the capacitor is flipped, but it's in the same configuration as it were before, just the charge is flipped. And so again, we get that all of the energy is in the capacitor. And so what happens for this circuit is once you close the switch, the energy will just slosh back and forth between the capacitor and the inductor. And the total energy is just the sum of the two. So initially, you start off with all of your energy in the capacitor. As that capacitor drains through the inductor, the current increases and the charge decreases. So the inductor gains energy and the capacitor loses energy. Once the capacitor reaches zero charge, the inductor, there's nothing to provide more current because the capacitor is empty, but the inductor doesn't want to let the current go to zero because that would mean reducing the flux through the inductor by Lenz's law. And so the inductor keeps the current going, which forces more of the positive charges to go around to the other side. And eventually, the positive charges on the other side of the capacitor will accumulate and gain more and more energy as the capacitor gets more and more charged. And eventually, it will overcome the energy, or it will overcome the repulsive force on that side of the capacitor, will overcome the induced electromagnetic field from the inductor, and it resets just with charge on the right side of the capacitor now instead of the left side. But so that's how an LC circuit works. It's just a balancing act between charge and current. Charge being the energy storage device for capacitors and current being the energy storage device for inductors. Now, the way that the energy is described then is you could either describe it in terms of the total energy you could either describe the total energy as the energy in the capacitor when the capacitor has maximum energy, or when the inductor has maximum energy. So in this case, U total is Q naught squared over 2C. That's the energy in a capacitor when it's fully charged, but it's also 1/2 L Imax squared. And so you can relate the total energy to either of these things. And again, this hopefully isn't surprising. There is a good example of this in the Liber text involving an LC circuit. It's example 5.4.1, and I suggest you check it out. Right, so that's all there is to LC circuits. They're pretty simple. They just are harmonic oscillators, and they just have energy passing back and forth between capacitors and inductors. By the way, this never stops, and that's because there's no resistor here to dissipate energy. This is an ideal system. In a real world system, you can't actually make perfect LC circuits because all conductors have some amount of resistance, except superconductors, I suppose. So the last circuit to talk about is an Lrc circuit. So an Lrc circuit is just exactly as it sounds. It has an inductor, a resistor, and a capacitor. So we're going to combine all of the above. And by the way, all of these circuits that we're talking about, we could have done the same thing and also include a battery. It would just change the differential equations as you might expect it to. You would have a plus EMF term. But we're just dealing with the simplest case. So the example that we're going to do here is you have your charged capacitor. And the reason why we have to start off with something charged initially with a capacitor charged is because we need something that's static that can kind of just maintain its energy until we close the switch. And we don't want to have a battery. Then we'll connect a resistor, an inductor, and then a switch. So initially, the capacitor is just holding onto its charge until we close the switch. So just as before, we have that Q of t at 0 is equal to Q naught. That's just the initial charge. So we have to use Kirchhoff's loop rule. So the loop rule, again, we're just going to make the same assumptions that we did before. We're going to assume that the current flows clockwise, and we're going to go through our loop, that the current flows counterclockwise, and we're going to go through our loop counterclockwise. We have L, R, and C, sorry. And so we can just write out the equation. So starting off at the capacitor, we get Q over C. Then because the current is flowing down through the resistor and we're passing by the resistor downwards, we get a minus IR. And then for the same reason as before, the inductor tries to prevent the current from increasing from 0 to not 0. So we get plus and minus on those sides of the inductor, at least initially. And so we get a minus L di dt. equals 0. And that's our Kirchhoff loop rule equation. So again, we still have this fact that the current leaving the capacitor is equal to the negative rate of change of the capacitor. This is just like above. We have that I is negative dq dt. So we can simplify our equation by plugging that in, writing it all in terms of Q. So we have Q over C plus R times, this is fine, plus R times dq dt. The minus sign goes the way of the dodo because we have a minus sign because I is negative dq dt, plus L d squared Q dt squared equals 0. And now we just have a differential equation involving charge and the three constants. Now this differential equation is harder to solve. That's just a reality of the situation. It's not impossible to solve. Like, there are techniques, and once you take a diff-EQ class, or maybe you're taking it now, you will learn how to solve equations like this. It's not like super esoteric, but it's not something that we're expecting you to know right away. But the point is the solution has different properties depending on the parameters. Like, it has qualitatively different properties depending on the parameters. And so what I mean by that is, in the harmonic motion of the LC circuit, if you changed L and C, the only thing that changed is it sped up or slowed down, right? The oscillation, it just got faster or slower. But here, if you change R, C, and L, you can actually get different qualitative properties. For example, if R is really small, if R is very small, then this circuit behaves a lot like an LC circuit, right? Because then the resistance has a negligible effect. And so then we call the system, so actually, let me rephrase. So then the system undergoes damped oscillation, or decaying oscillations. And maybe you could have guessed this. It would behave almost exactly like an LC circuit, except some of that energy goes away every cycle. And so the amplitude of those oscillations, the amount of current, the amount of charge, that decreases just a little bit every cycle because the resistor is there to dissipate energy. It undergoes decaying oscillations, and so we call a system that has those properties, we call it underdamped. So if R is just right, if it's just barely large enough to prevent oscillations, i.e., rather than the resistance being low enough that the capacitor can drain into the inductor, then the inductor will go back to the capacitor and so on. It's just barely big enough that it just goes straight down. Then to prevent oscillations, and I'll draw a picture about this in a minute, then the system is called critically damped. And then similarly, if R is too large, if it's larger than the critical dampening value, then the resistor just dissipates energy too quickly and the current never oscillates. So that's what I mean by different behavior depending on the parameters. You can have two LRC circuits with different values of resistances and capacitances and inductances, but they're otherwise the same circuit, where one of them oscillates back and forth for a good while and the other one just goes to zero after however long. So in that case, where R is too large, this is called overdamped. Clearly, physicists are very clever with our naming conventions. So the picture here, if I were to draw charge as a function of time in, say, the underdamped and the overdamped, the charge might look like this. This might be an example of an underdamped system, if you were to plot charge over time. And if you were to plot charge over time for a critical or an overdamped system, and by the way, in the critical and overdamped case, it's a little bit harder to tell them apart. But in that case, the charge just goes like that, just dies off exponentially. So, and we can actually express when these things happen mathematically by, again, these depend on the properties of the equation, and you can go back and count and solve the equations and figure out where these come about. But the mathematical way to relate these notions to the constants is as follows. You have an underdamped system when r squared, so if you take the resistance and square it, is less than 4L divided by C. You have critical dampening when r squared is equal to 4L divided by C, and you have overdamped systems, as you guys can probably guess, when r squared is greater than 4L over C. So depending on what these parameters are, you will get different behavior. And this is exactly how you can characterize that behavior. Now, there is something to be said that if r squared is just slightly less than 4L over C, it will be close to being critically damped, meaning that the oscillations will be very small. It'll oscillate, like it will technically oscillate, but it might just go like this, just a little bit. Whereas if r squared is so much smaller than 4L over C, then you'll get basically infinite oscillations. So that's the basics of an LRC circuit. And this is really how a real life RC circuit or LC circuit would behave. It would actually oscillate like this. Now, if you have an energy source, if I put, say, a battery here, then you can actually produce perpetual oscillations. And, that's how you can make like signal generators and things like that. And how you can, create antenna and things along those lines. But that's not in my wheelhouse. You'll have to go to engineering school for that, to learn more about that. I mean, like to learn more about like antenna shapes and things like that. If you want to talk about putting a battery in a circuit, then I can answer that question. But that's it about circuits. So congrats, you guys passed through circuits. You're done, or at least you might be done if you're not an electrical engineer. Last thing to talk about today is something that I kind of shoved under the rug, and it was even sort of on a quiz question, but with what you knew at the time, the quiz question was valid, and that's this issue with Ampere's law. So you may have already thought that Ampere's law is kind of weird because there was this business about Ampere's law not working super well for a finite length segment of wire, and it does, assuming you, or if you assume that the electric field, if you assume that that it's not technically enclosed, if the electric field is, it's not technically enclosed if it's a finite length of wire. We talked about that when we were first talking about Ampere's law. But there is a way to fix it so that we actually know what to do, so we don't just have to worry about things not being enclosed. So there is a way to fix this. So the issue is, if charge builds up, if charge is allowed to build up on either end of a finite segment of wire, how do we apply Ampere's law? And the reason why we care about that is because for a finite segment of wire, if there's current flowing through, that means that if you have a wire that's oriented vertically, you have current going this way, that means that you're going to end up with negative charges on one end and positive charges on the other end. And so that's why there's a problem in Ampere's law, because we don't really know how to handle that yet. And so the question is how do we fix Ampere's law so that it accounts for that fact that we have a buildup of positive charge and negative charge on either end? And I'll explain in a little bit more detail in just a second. So what we're going to do is, instead of talking about a finite segment of wire, which would work, it's just a little bit messier, we're instead going to kind of idealize a way, and we're going to imagine applying Ampere's law to an infinitely long wire that has a break in it. And on that break, we have two capacitive plates. So the example here is consider an infinite wire with a capacitor somewhere in the middle. So the picture here is you have your infinite wire, you have your capacitor, and you have the rest of your infinite wire going down forever. So we know that Ampere's law applies for infinite wires. So putting a little small break and then capacitive plates shouldn't affect what's happening infinitely far away on the other end of the capacitor, right? So it shouldn't like there should be no net effect to using Ampere's law. You should just be able to put a loop around it and then find the magnetic field. But there's an issue. So remember that the way that we defined the enclosed current for a loop was we imagined that you like stretched a balloon over your loop so that the edges of your loop are the, this surface. And then we asked how much current went through that surface. But you can stretch that surface however you want. And so because the piercing surface, which is what we are interested in finding the amount of current passing through it, that did not make sense, but you guys get the idea. Because the piercing surface can be deformed, we can place the surface through the gap in the capacitor. I'm going to do my best to draw this, so bear with me. I'm going to draw a better picture. So we have our wire. We have our capacitor, and we have our wire continuing on. This is a blown up version. So let's say that our loop looks something like this. Let's say we want to find the magnetic field around that loop. We would typically use Ampere's law. We would figure out that, the amount of current that's enclosed is just the amount of current that passes through the loop if it's just flat. But you can imagine, instead of having just a flat surface that the current passes through, you can imagine instead making your surface bubble out like this. And now there's no actual current flowing through it, right? Now, because the loop is wrapping around through the gap in the capacitor, current doesn't cross the capacitive plates. You get charge buildup on one plate and charge buildup on the other plate, but no actual charge passes through that surface. So the issue is that if you use one surface, you would get one answer, which, if you use the green surface, you would get the one that involves mu naught I enclosed. If you use the other surface, then you would say that you would get 0. But we know they should give the same answer because they are the same surface integral, or they have the same left-hand side. Let me draw some charges here because that's really what's happening. You have charge buildup on one side, charge buildup on the other side. You have current flowing up. So we need to fix Ampere's law so that regardless of which surface you choose, the green one or the purple one, you get the same answer on the right-hand side. So we should have that b dot dl. So this part of the integral, that doesn't care about the surface. That's just the blue line, right? We should have that this is equal to mu naught I enclosed. And I'm going to put I green. But that should also be equal to mu naught times something equal to I enclosed that doesn't depend on actual current flowing through it, right? Because there is no current flowing through that surface. So the question is what could this stuff be so that if we had chosen the purple surface instead of the green one, that we get the same answer? That's what we need. So it turns out that there is something that is happening in the region where the purple surface is passing through, right? We know that because there's current flowing into this capacitor, we know that there's charge being built up on that capacitor. We also know that the charge is affecting or is producing the electric field between the capacitive plates. And so we actually can see, now I'm running out of colors. Let's use orange. We can actually see that as charge builds up in the plates, we start producing electric fields that pass through that surface. And so what we can do is we can relate the rate at which, or we can relate the current flow to the rate at which charge is accumulating. And hence we can relate that current flow, or because the rate at which charge is accumulating, because the charge is accumulating, we produce electric field, we can relate the current flow to the rate at which the electric field is changing in time. So, as a quick reminder from earlier in the course, the electric field inside a parallel plate capacitor is just sigma over epsilon naught, where sigma is the charge density. And we know, assuming it's a parallel plate capacitor and everything else being equal, we can find sigma by just dividing the total charge on the capacitor by the area. So this is Q over epsilon naught A, where A is the area of the plates. Further, the current is going into the capacitor, the charge is increasing. So the current is just dq dt. So the current that passes through the green surface, that's equal to the time derivative of epsilon naught times E times A. Now, how did I get that? Well, I solved this equation for Q, and then I plugged that in here, and then I took a time derivative. But this should look awfully familiar. A magnitude of a vector times an area. Well, indeed it is. This is just epsilon naught times d dt of an integral of E dot dA. This is the electric flux through that purple surface. So if we wanted to use the purple surface instead of the green surface, we would have to, instead of writing mu naught times I, we would write mu naught times this stuff, because this stuff tells us it's precisely equal to the current flowing through the green surface, but it's written in terms of stuff that the purple surface knows about, because the purple surface is passing through the capacitor where there is a changing electric field. So this quantity here that I've just written out, the time derivative of the electric flux times epsilon naught, that has a name, and it's called the displacement chart, or the displacement current. And the reason it's called that is because the change in the electric field behaves precisely as if we had taken the current passing through the green one and had put it here. So there's no actual current passing through the purple. Yeah, we'll get there. There's no actual current passing through the purple surface. There's just an equivalent amount of change in electric field, which is exactly how much you would expect if there was exactly as much electric field change as you would need to account for some amount of current. So more generally then, we can actually fix Ampere's law by combining both of these effects. So if the E is changing and there is current piercing the surface, for whatever reason, maybe you have a more complicated system. So maybe there's current passing this way. Maybe your system involves some current also going out this way. So there'd be current passing through the surface and there's an electric field changing. We have the following. And now we're just going to combine both effects. So in the case of the green surface, there was no changing electric field and there was all enclosed current. in the case of the purple case, there was no enclosed current and all electric field, but we can combine them into the full Ampere's law. So this is Ampere's law with displacement current, or also known as with Maxwell's correction. So the Maxwell equations, which you may have heard of and which we will get to today, the reason they're named after Maxwell is because Maxwell kind of put them all together into a nice coherent notion, but also fixed Ampere's law. That's where he gets a lot of his fame from. And so this can be written as the integral around the loop of the magnetic field. This is equal to mu naught times I enclosed plus the displacement current. And that displacement current, we can rewrite this, it's just I enclosed plus mu naught epsilon naught d dt of the integral E dot dA. So really, Ampere's quote unquote, Ampere's true law is this one in a box. The only reason why we didn't use this before is because we didn't have a situation where the electric field was changing, and we didn't really know how to handle that yet. And so we can also, just so you guys remember, whenever we talked about these new laws, when we talked about Ampere's law, Faraday's law, Gauss's law, whatever, once you have an integral form, this is an integral form, it has an integral on both sides, and even this current, that's really just an integral over the current density, J, you can write them in terms of a local form using either Stokes' theorem or the divergence theorem. In this case, it's an expression about Stokes' theorem. And we're going to rewrite this much the same way that we used the Ampere's law without Maxwell's correction. So the local form becomes, so it's you still have the curl of B on the left-hand side, and you still have mu naught J on the right-hand side, but now we have one more term. We have plus mu naught epsilon naught d dt of the electric field, the time derivative of the electric field. That's this last term here. This is the local form. This is the local corrected version. So by the way, when we talk about this correction, this is sort of like when we talked about the curl of E. So initially, at the very beginning of the course, when we were talking about electrostatics, there's this notion that the curl of the electric field should be 0. But then we said, oh, but wait a minute, what if the magnetic field is changing? Then you have some magnetic flux, and then you can have some non-zero electric curl. The same thing is happening here. It's just there was already a term that was there, so we just had to add one extra term that accounts for the changing electric field that can produce more magnetic curl. And so what this formula tells us is that a time varying electric field, this is just like Faraday's law, by the way. Faraday's law says a time varying magnetic field causes an electric field. This is the statement that a time varying electric field causes a magnetic field to circulate. The difference here is that that's not the only thing that can cause a magnetic field to circulate. In fact, current makes a magnetic field circulate on its own. You don't need a time-varying electric field, whereas you need a time-varying magnetic field to get a circulating electric field. Right. So this is so hopefully you see by now that there's like a nice duality between the electric field and the magnetic field. There's some differences. For example, the divergence of the magnetic field is always 0, and the curl of the electric field doesn't have a term that looks like mu naught J. It just has the time varying part of the magnetic field. But there is some duality here. And so one of the things that Maxwell got his name on, like the big thing, is his equations, Maxwell's equations. So I'm going to write those out in a sort of in a table, just so you can see how similar they all are and how self-dual they are. So we have our law over here. We have our integral form. And then we will have our local form. So this is just a summary of all of the laws that we've talked about up till now. So there's Gauss's law. This is the electric version. Gauss gets two of his laws in Maxwell's equations. The integral form is just that the electric flux is equal to the enclosed charge divided by epsilon naught. And the local form is a statement about the divergence of the electric field. It's equal to rho over epsilon naught, the charge density. Then there's Gauss's magnetic law. Which is a similar statement. It's the magnetic flux through a surface. And Gauss's law for magnetism, just zero, says that there's no magnetic monopoles. And so the local form is just that the divergence of the magnetic field is zero. Then there's Faraday's law. So Faraday's law in integral form is that it tells us about the circulation of the electric field. And Faraday's law tells us it's the negative time derivative of the flux, or put another way, it's negative d dt of the integral of b dot dA. And so in local form, that's the curl of E. Remember, curl tells us about circulation, and divergence tells us about flux. This is equal to the time derivative of the magnetic field with a minus sign. And then there's Ampere's law with the correction. With Maxwell's correction. And this one's the longest one, unfortunately. So it's an integral of b dot dl, it's the circulation of the magnetic field. This is equal to mu naught I enclosed plus mu naught epsilon naught ddt of E dot dA. Kind of long, sorry. Maybe I'll put that on another line. Put it down there. And so the local form, again, it's also the longest one. It's the cross, or the curl of B is mu naught J plus mu naught epsilon naught dE dt. And so those are Maxwell's four laws, or Maxwell's four equations rather, not Maxwell's laws. Those are the set of four equations that make up Maxwell's laws, or Maxwell's equations, and they are like probably they're not quite the first like mathematically rigorous explanation of physical phenomena, but they are probably the first mathematically complete explanation of physical phenomenon. Now I say complete, they're not quite done. This tells us how the electric field and the magnetic fields behave. How they behave in the presence of charges and moving charges. It doesn't tell us how those charges and moving charges behave in the influence of these fields. And we'll get to that in just a minute. But first I want to show you the power of these laws, what makes them, like why we care about them. And this is just one simple example of how we can, of a consequence of Maxwell's equations. So let's talk about charge conservation. So remember when we first talked about charge conservation in this course, there was an equation that related the divergence of J to the time derivative of the charge density of rho, and that gave us the charge conservation equation, or the continuity equation is another name for it. And it turns out that you can actually derive that equation from Maxwell's equations. So just as a quick reminder, this is a vector calculus identity. If you take the gradient of the if you take the divergence of the curl of any vector field, you get 0. So we're going to use that. So in particular, the divergence of the curl of the magnetic field, that just has to be 0 because it's a vector field. And so, but we know what the curl of the magnetic field is. It's from Ampere's law, the local form. It's mu naught J plus mu naught epsilon naught dE dt. That's all equal to 0. So that is, we get that the divergence of J, I'm factoring out a mu naught and dividing, by the way, plus epsilon naught times the time derivative of the divergence of E That's equal to 0. So we can change the order of these derivatives, by the way, because one's a spatial derivative and one's a temporal derivative. And generally, at least until you get into general relativity, you can swap the order of those, no problem. And then we can use Gauss's law to relate the divergence of the electric field to the charge. And so what we end up with the divergence of J plus d rho dt. That's equal to 0. And this was the continuity equation, or the charge conservation equation that I gave you guys earlier. So built into Maxwell's equations is charge conservation, which is already a really strong indicator that this is a complete set of equations that govern a particular phenomenon in our universe. We don't have to add a whole lot more. Now, I did say that this doesn't tell us how charges behave under the influence of the of these fields. And so you can include that in two ways. So you can include that in two ways. One of them is obvious, or the influence on charges, I should say. One of them is just you give your set of Maxwell's equations, and then you also specify, like if you want to fully describe a system, you need your Maxwell's equations, and then you need the Lorentz Force Law, which is the following. It's just that the force on a charge is Q times E plus V cross B. That would be enough. That would tell you, so Maxwell's equations would tell you what E and B are, how they relate to the charges, and the Lorentz Force Law will tell you how those charges relate to the electric and magnetic fields. Now, it would be a little bit involved if you have moving charges that are creating their own electric and magnetic fields and all interacting with each other, but in principle, it's fully described. Alternatively, you could also just specify the potential energy. You could specify the potential energy of the EM fields. So rather than specifying a force, you can specify the energy that a charge, or that the fields have, which will tell us how much energy charges will have in different places. So this is just 1/2, and we already know the energy in an electric field. It's 1/2. This is energy density, by the way. 1/2 epsilon naught E squared. We know the energy density in the magnetic fields. It's 1/2, or it's 1/2 mu naught times B field. So the total energy is just the sum. Total potential energy. So you can specify either of these. That E is ugly. You can specify either of these, either the potential energy density or the force, and they will give equivalent information about how the charges move in the system. The Lorentz Force Law is a little bit more obvious how it tells us how the charges move, because we know how charges move. Like if you give a force, you can just use Newton's law to figure out how the charges move. But the potential energy density also tells us how charges move, because we know that charges, we know that objects tend towards reducing their potential energy, and so the charges will move in such a way so that the potential energy is reduced. And so if a charge starts moving, it will create more magnetic field, which will increase the potential energy, and so on. So both of these equations, either A or B, they both include all of the information about how the fields affect the charges. Right, okay, so that's great. So those four equations, either the local form or the integral form, they're equivalent. And then either one of these 100% specifies how things experience electricity and magnetism. Now, for the most part, our entire universe is governed by this. There's a few exceptions, like the nuclear fusion that occurs in the heart of every star that drives life on this planet. That's kind of important. It's not governed by electricity and magnetism. But like anything that really happens on Earth, with the exception of, I guess, radioactive decay, like me picking up a pen, or me, like the force between the electrons in my hand and the electrons in this pen that keep them from touching, that is mostly explained by electricity and magnetism. There's something to be said that quantum mechanics is required because there's some Pauli exclusion there, but for the most part, like literally everything is governed by these laws. And so that's why people thought that, you know, these were kind of codified in like the late 1800s. That's why people kind of thought, well, physics is done. We're just done with physics now. Everything's these four equations and then one of these two equations. it turns out that they were mistaken for good reason. But the first thing that they didn't really, and this was another of the third thing, or this was probably the third thing that Maxwell is super famous for, is that he not only wrote down and codified these equations, he also was able to explain another phenomenon with them. So first, let's talk about wave propagation before I close that cliffhanger or take you off that cliffhanger. So as I established earlier, if you have a time-varying electric field, that can produce or induce a magnetic field, and vice versa. So thanks to Ampere, Maxwell, and Faraday, we know that changing electric fields can induce magnetic fields, which can induce electric fields. So if you change the electric field, the magnetic field will be created. But if there was initially no magnetic field, and then you start changing the electric field, now the magnetic field goes from 0 to not 0. So the magnetic field is changing. And that changing magnetic field can produce a field. And so it will cause the electric field to change, which will then cause the magnetic field to change, and so on and so forth. So Maxwell had the idea, and this was a really clever idea, that it might be possible to have self-propagating fields. If you set up the initial conditions just right and then take them away, it might be possible for those electric and magnetic fields to just keep affecting each other and keep them going forever. So he put this to the test. He was a clever mathematician, so he checked this. So we're going to basically go through what he did. He had a lot more horrible notation than what we currently use, by the way. Modern calculus notation makes it a lot easier. He had a lot more work for him. So if you're curious, you can actually go look at what like Maxwell's notes look like, and they're awful. Like he's doing everything in terms of components. It's terrible. Anyway, but we can just write down Maxwell's equations. So let's consider Maxwell's equations in a vacuum. So what that means is we're considering it in the presence of no charges and no currents. So then Maxwell's equations simplify a lot. There's the rho isn't there, the J isn't there. So Maxwell's equations in a vacuum, and this is the local form of course, become the following. Gradient of E is, sorry, the divergence of E is 0, the divergence of B is 0, the curl of E is negative dB dt, and the curl of B is mu naught epsilon naught dE dt. And by the way, hopefully now you can actually see the symmetry between that's a terrible mu, between the electric and magnetic fields. Why we call this electricity and magnetism, or electromagnetism, rather than just there being a course on electricity and a course on magnetism. They're very clearly related because like they look like just two sides of the same coin. And so we can actually apply these equations and just start doing stuff to them. So let's take the time derivative of the curl of B and then just see what happens. So we have ddt of the curl of B. This is using the last of our equations, Ampere's law, with Maxwell's correction. Well, sorry, no, we're going to use Faraday's law first. This is the curl of the time derivative of the magnetic field. Again, you can swap the time and spatial derivatives. And then we can use Faraday's law. Sorry. Yeah, hold on. I need to make sure that I'm getting this right. Why did I write it that way in my notes? It's very clearly what, yeah, don't worry about that. We're just going to use Faraday's, or use Ampere's law. We know what the curl of B is. So that's mu naught epsilon naught times the time derivative of E. So this is just equal to mu naught times epsilon naught times 2 time derivatives of the electric field. Now, there's a little bit more that can be done. We also know that this is equal to the curl, this is why I wrote it in my notes, of the time derivative of b, right? And the curl of the time derivative of b, well, we know what the time derivative of b is. That's equal to the curl of e. So this left-hand side is also equal to the negative curl of the curl of e. And so what we're left with is the negative. So I'm using both of these laws to rewrite the same thing in 2 different ways. So we're left with the equation negative curl of the electric field is equal to mu naught epsilon naught times 2 time derivatives of the electric field. So already we have an equation that just relates the electric field to itself. Now we're not quite done yet. There's a vector calculus identity that we need. We can actually simplify that curl of a curl. Turns out that the curl of a vector field is equal to the gradient of the divergence of that vector field minus the divergence gradient. This is also known as the Laplacian. This is basically d by dx squared plus d by dy squared plus d by dz squared on each component. And so because from Gauss's law, because the electric field has no divergence when there's no charges around, we get that this term vanishes and we're left with minus Laplacian of the electric field. And so we can plug that back in here and we get the following equation. We get that the Laplacian of the electric field, the minus signs cancel out, is equal to mu naught epsilon naught times the second time derivative of the electric field. And now that's an equation that should look awfully familiar. So this is the wave equation, but for a vector field, right? So this is the wave equation for every component of a vector. So you'd have Ex, Ey, and Ez, and you'd have, on the left-hand side, you'd have d by dx squared on Ex plus d by dy squared on Ex plus d by dz squared on Ex equals mu naught epsilon naught d by dt squared on Ex. And then you'd have that for all 3 components. And Maxwell noticed this. This was the thing that really put him on the map. And so the question then is, how fast does it travel? So we know that wave equations have corresponding wave speed. And so the question is, what is the wave speed for this electric wave? Well, we know, hopefully you guys learned this in 9B, that if you have a wave equation, then you can extract the wave speed by taking, well, the typical wave equation has a 1 over v squared times d squared e dt squared, right? And so we can extract this speed just by looking at our wave equation. And that gives us a wave speed of 1 over the square root of epsilon, or of mu naught epsilon naught. And we know what the numbers are. We know what those numbers are. We can calculate them. And it turns out that this thing is 3 times 10 to the 8th meters per second. And you should, like, hopefully you recognize that number. That's the speed of light. And Maxwell knew that too. He also knew that that number that he just calculated is the speed that they had measured light to move at. And by that point, they had measured the speed of light. So he had an aha moment that, oh, these self-propagating electric and magnetic fields that can propagate one after the other, that's what light is. That was his big idea, and that's why he's super, super famous. And by the way, you can repeat an identical process to derive an identical equation for the magnetic field. You would just start with the curl of the electric field. You would write the curl of the electric field in terms of the rate of change of the magnetic field. You would also write it in terms of the curl of the magnetic field, and you would just do the same process, and you would end up with an identical equation with an identical wave speed. So the conclusion then is that light is an electromagnetic wave. And the reason it's electromagnetic is because the only way that you can have the self-propagating wave phenomenon is if the electric field changes to produce a magnetic field, which then changes to produce more electric field. So they're linked up together. You can't have a self-propagating electric field on its own. It requires a magnetic field that also propagates with it. Now, there's a little bit more to talk about. This wasn't originally in my notes, but I figured I would go over it. We can actually kind of, like now that we know that the electric and magnetic fields propagate as a wave, maybe I'll put a box around this because that's kind of the culmination of this course. We can actually just start doing some calculations and just treating it kind of like we know how to do. So let's look at an example of just a solution to the wave equation. So let's just work an example and see what happens, see what we can learn. So let's use a harmonic plane wave. So what we're going to do is we're just going to assume a solution for the electric field and then see what happens. So we already know what the form of what the formal solution is for a wave, so we can guess pretty well. So we're going to let the electric field be, so it's pointing in the I hat direction. It has magnitude epsilon naught, or amplitude, sorry, and then it has the harmonic wave part. And let's say it's moving in the z direction. Z direction for those non-North Americans. So it's 2 pi z over lambda minus 2 pi t over capital T, where capital T is the period, lambda is the wavelength. And by the way, you could go and you could just plug this in to this equation, and you'd find that it works. And this equation actually gets a lot less interesting in this case because there is no y or z component. There's only the x component. So this just becomes the Laplacian of the x component of the electric field equals mu naught epsilon naught times the second time derivative of the x component. And then that's just a normal wave equation that you guys have all seen before. And it only varies in the z and t component, or in the z, it only varies with z and t, so the derivatives with respect to x and y just don't play a role. So it becomes relatively straightforward. And you could just check by just plugging this in. So, okay, so that is a solution. So let's figure out what the magnetic field looks like. So then the curl of the electric field, we know how to take curls. We know what this electric field is now, so we can just take the curl. It works out to be the partial derivative of the z component, sorry, of the x component of the electric field with respect to z in the j hat direction. So we can just take that partial derivative. So this is minus 2 pi over lambda E naught times sine of 2 pi z over lambda minus 2 pi t over capital T in the j hat direction. Okay, that's the curl of E. Then we can apply Faraday's law. We can relate the curl of E to the rate of change in the magnetic field. So the curl of E should be equal to the minus time derivative of the magnetic field. And we know what the curl of E is. So you can, if the minus time derivative of the magnetic field is equal to this thing, this is the land of the long equal sign, then you can just do an integral with respect to t to find out the magnetic field. That tells us that the magnetic field also varies with z and t, is j hat times t over lambda E naught times cosine of 2 pi z over lambda minus 2 pi t over t. And so we learn something from this. What conclusions can we draw? So the electric field and the magnetic field have the same wavelength, and period. Also, and this is more 9c material, because lambda over t is equal to the speed of propagation, in this case c, the speed of light, we see that the magnitudes of these, or the, let me say the amplitudes, so b naught, which we're defining as just this stuff, is equal to E naught divided by C. So that tells us if the electric field has this magnitude, then the corresponding oscillating magnetic field would have that magnitude. And then we also learn that the electric field is perpendicular to the magnetic field, because the magnetic field is in the j-hat direction, the electric field is in the i-hat direction. So we can conclude a lot just from this simple example, and you'd find that if you tried a more complicated example, like a wave pulse or a photon packet or something like that, you would find that this is still the case. You still have that the electric field is perpendicular to the magnetic field. You still have that the magnitude of the electric field is related to the magnitude of the magnetic field, sorry, the amplitudes, by a factor of 1/c, and we would still have the case that they have the same wavelength and periods. Then there's notions of polarizations, which you've talked about in 9b and so on, but I'm not going to spend a whole lot of time on that. So that's stuff about light. And at this point, now you can just use all of your understanding from 9b to discuss light even further. So we don't have to talk about that. That's not content of this course. So that takes us through to the end. That's all I had for you guys today. I'm going to end the lecture here, and I will be more than happy to take questions.